Hello, and welcome back to another episode with It's Dr. Dan. And today we're going to be looking at isotopes. And more specifically, we're going to learn how to write isotopes and how to solve percent abundance and atomic mass problems, which you will most likely see in your first semester of general chemistry as a homework problem or as an exam problem. So we definitely want to make sure we master that to get all the points that we can to pass chemistry. Now, what exactly is an isotope? Well, for all kinds of different atoms that are out there, if you go to the periodic table, you'll see that every one of them has an atomic mass, but they have a bunch of decimals behind them. So what an isotope is atoms that are the same element, but they have different atomic masses, meaning that when we have all these individual isotopes, they have different numbers of neutrons. So, which can be really confusing for a first-time student, and maybe it still doesn't make a lot of sense. So let me try to explain this to you, so that way you are able to follow along. The basic idea behind it is sort of similar to this example here. So right here, I have three different pies. They are actually all the same exact pie, but I changed their size, meaning I changed their mass. So if I have a pie and I look at this, my first pie is the little one. He weighs about 100 atomic mass units. Great. And then my next one weighs 150 atomic mass units. It's still the same pie, but it's just bigger. That is all. Now, if I have another one, it's heavier as well, 200 atomic mass units, but they're all the same exact pie. They are just different sizes. Atoms that are different isotopes are like the same thing. So whenever they have a different number of neutrons, so kind of referring to more the right-hand pie, right? So this one has more neutrons. This one over here on the left has less neutrons. It's a similar idea. So just by adding more neutrons or less, the mass is going to go up and down as a result. Now, being that there is a different amount of these that exist in our world, right? We have all kinds of different sizes of pie, different size elements. There is a certain percentage of them that exist. And based on that is how those average masses exist. So let's try to dive into this and see if we can understand this world of isotopes, just like the pie example. Because life is a big slice of pie and we're going to try to understand it, right? So let's get into it. All right, so back to where we were at before. The thing about the take-home message from our example was that isotopes always have the same number of protons, meaning they are the exact same element. So like before, they were the exact same type of pie. The same element will have the same number of protons, but their masses will change. So whenever we see this, more neutrons means more mass, which is a heavier atom. Whenever we have a lighter atom, that's less mass and fewer neutrons. So more is heavier, less is lighter and fewer. So whenever we're looking at the periodic table, let's say if we look at carbon, for example, like I have here, well, the atomic mass is included in the information found on the periodic table. However, this value here is an average, right? So what we are seeing here is that 12.009 is an average mass. So when we are looking at all these, it's an average. It does not completely and accurately show each individual isotope. It's an average of all of them, or a weighted average of each individual one. In fact, carbon has multiple isotopes. And let's try to get into this to be able to see exactly what this is going to look like. Every single isotope of an element is identified by the mass number, meaning that the mass number is equal to the atomic number plus neutrons. Now, why is that? Well, if you remember from your chemistry class or from my previous videos, the atomic number is equal to the number of protons. And being that protons and neutrons are the heaviest component inside of the nucleus, this is what rules our atomic mass. They both equal approximately 1 AMU or 1 atomic mass unit, both that and neutrons. So what we do is the format that we write all this looks a little bit like this, where we write the mass number in the top left corner, we write the atomic number in the bottom left, the charge in the right, and you might see it very much written like this, where the atomic mass is written by the letter A, the atomic number is written by the letter Z, you have your element symbol, and then your charge, which if there is an ion form of it, so either a cation or an anion. Let's do an example of how this will look. Let's go back to our carbon example. So if we had carbon, right, there, like earlier I mentioned, there's multiple isotopes, there's 3 of them. So let's practice writing all 3. So if I have carbon, right, so we write down our element, right, which is this letter C. The first thing you got to do is, what is your atomic number? So when you look at your periodic table, you'll quickly see, and from what was up from above, that the number for that was 6, right? So we have a atomic number of 6. Now, being that I mentioned we have 3 different isotopes, we're going to write all 3 of them. Now, the thing that's important here is, even though they're all different isotopes, and notice how they're slightly increasing in size, is that they all have the same number of protons, which is the most important part. They have the same number of protons. Now, the next part is your mass. So for carbon, there's carbon 12, carbon 13, and carbon 14, which is referring to their masses. So when we write these, we can write carbon 12, 13, and 14. Now, what exactly does this tell us? Well, when we look at that, if you remember, the atomic mass is equal to protons plus neutrons. Also, when you have your atomic number, this is equal to the protons. So protons in this case is 6. This is your protons plus neutrons. So you can kind of do some little simple algebra to be able to tell you how many neutrons are there. So for example, for carbon 12, we have 6 neutrons. For carbon 13, we have 7. And for carbon 14, we have 8 neutrons. So it progressively gets a little bit heavier as we go from the left side to the right side. So it gets heavier because of that extra 1 neutron. It's like our slice of pie. As the pie got bigger, it got heavier. Same thing with carbon. We're adding an extra neutron each time. And most of the time, isotopes just differ by 1 to 2 neutrons. It's usually not a huge difference, but they could have an extremely different effect on how they behave within the world around us. By adding more neutrons, it could make it less stable, possibly radioactive, or it could even have beneficial effects that we can find all around in our everyday lives. So for example, a fun example of isotopes is in your smoke alarms at home. A lot of them have a Magnesium 241, which is AM 241. And it's a slightly radioactive compound, but once smoke kind of changes that little radioactive compound inside, it actually was what's going to set off your smoke alarm. So it's nothing that's harmful to you, but it's just kind of a cool thing to see that there's an isotope being used even in your own house, whether you realize it or not. Some other different examples too of this is, let's say if I want to write oxygen 14 ion. This is another way that you can illustrate how ions are written as well. So not only do we have that notation of the atomic mass with the number, and then our element with the charge, but you can also write oxygen 14 to help illustrate that, oh, this is still an isotope. So let's get at it. Let's try to write in that format that we had earlier. And being that this is an ion, well, we got to think of our periodic table. Oxygen is a nonmetal, meaning that it has a tendency to take electrons. So this is an anion, or if you think onion, because it makes you cry, right? It makes you sad. So that would be our anion example over here, right? So now going off of that, so how would we go and write this? Well, same as before, we'd write our symbol, being that it was given to us that this is oxygen 14, right? So we'll write that down. And now we got to look up what the atomic number is. So when you look on a periodic table, you'll quickly see that oxygen is number 8. Now, what is the charge tendency for this? Well, if you kind of think about how your periodic table is, this is 2 columns from the far right side. So what that is, or sorry, 3 columns from the far right. Fluorine's column is -1, oxygen is in -2, nitrogen is -3. So what this is going to tell us that this has a tendency to make a -2 charge for our problem here. And that's how you can do an ion, right? We can show the charge in this case, and that's the big difference. Let's go on to some more fun examples. Okay, another really kind of cool example is that isotopes are all around us. Even the simplest atom, hydrogen, has 3 different isotopes, which are commonly seen all around. And actually, all 3 of them have their own unique names to determine them in more of like a physics world, or even sometimes in organic chemistry too. Protium is the top one, which is our normal hydrogen that we use every day. We have deuterium, which is very often used in organic chemistry, or tritium is also used. Now, what is the difference? Well, with each of these, right, if you think of a first hydrogen, that's just 1 proton, 0 neutrons, and we're even showing that with our Bohr model by showing just 1 proton in there. Then for deuterium, well, we have 1 proton and now 1 neutron, which is being shown in blue inside of our little Bohr atom here. So there's our little neutron. And then with tritium, which is a little more unstable, we have 1 proton and 2 neutrons within inside of our nucleus. So the only thing that's changing is your number of neutrons. They're all hydrogen, every single one of them, being that the protons are what determine that this is hydrogen. The only thing changing is its mass and the number of neutrons here. So you can still see that these two, when we add them together, are equal to 1, that the 1 and 1 are equal to 2, and then the 1 plus 2 are equal to 3. So we still have that simple mathematics here of how those masses are about. Let's go on to percent abundances to be able to solve this next type of problem. Okay, now, like earlier that I mentioned, atomic masses are an average, right, of each of the individual isotopes that make up an element. So whenever we read our periodic table, for example, with carbon, right, the number that was on the periodic table is 12.009, which is a weighted average of carbon 12, carbon 13, carbon 14. So that is how these numbers are found. What we use to find it is the formula that's up here that's in this green box, which is atomic mass is equal to the relative abundance of each individual isotope. So what exactly does that mean? What is a relative abundance, or written with the letter F here? So relative abundance is a percent, meaning, oh, we got to remember our percents. And if that's something that you haven't quite mastered, please refer to my Math Skills to Ace Chemistry video on percents, which goes over all the key tips on how to use percents in chemistry. But the simple part of it really is that all we are going to do is, for the percent, is we take our number and divide it by 100, which will put it into decimal form. We'll use that number and we'll multiply it by the mass of its respective element. So you're always given the percent and the actual mass for that isotope. We take all those values and we add it to the abundance and the mass of the next isotope, and we keep going until infinity, until we run out of isotopes. It's a general idea on how to use this. So let's try and look at a specific example of how we can do this and what it kind of looks like. So in a problem like this one says, calculate the atomic mass of magnesium given the natural abundances and mass of each isotope below. So for a lot of these types of homework and exam problems, you're given a list of all the isotopes, which have the masses for each one. So we can see we have magnesium 24, 25, 26, right? And we have a mass for each individual one. And then they also have their percent abundance. Now keep in mind, this is a weighted average. So what that means is it's very similar to how your grades are calculated in your classes. So for example, maybe in your class, 25% of the grade is homework. Maybe 10% is the final, 30% is an exam, but each one of them has so many points allotted to those categories. However, it can't go over that specific percent. It is weighted, right, for your final grade. It's kind of a similar idea here. Every single category has a percentage that goes with it, and we add up all the points, which is where your mass is. So let's try to do this using our formula. Now, my big tip here is we got to convert each of the percentages to decimal form. Okay, so our first step is what we're going to do is start plugging in our values into our equation and then convert things into percents as we go. So we have our atomic mass, which is going to be equal to each individual isotope. So for the first part, we have our first line, which which I'll do in purple to match sort of the colors. So we have 23.985, which is our mass, and then we'll multiply that by the decimal of our percent. So we're just dividing 78.70 by 100 to get it into that decimal form. So that would be number 1. So this is isotope 1, or we can even label it as isotope Mg24. Now what we're going to do is do the next one, which is isotope Mg25, and plug that into the equation as well. So we'll take 24.985, multiply that by 0.1013, which is our percent, once again, converted. And then we will close our parentheses, add that to the next isotope. So the line will continue down here. And once again, we'll take that relative abundance times our mass. So we got the mass of 25,982. So we're just doing this third line here. And then we'll multiply that by 0.1117. And that's how we'll do that. And just as a reminder, the way that we got this number is 11.17 divided by 100. So that's percent to decimal. It's how these numbers are coming up. So we'll take these numbers. When you are putting them in your calculator, make sure you are using percents for each individual part. So that, or sorry, not percents, use parentheses for each individual part. So that way it gets added up correctly. You don't want the order of operations to get accidentally crisscrossed and messed up by accident. Always use parentheses. So when you do that, your final answer is going to be 24.31 AMU. And you'll see that it actually matches very closely to what you will find on your periodic table, which is also 24.3. Keep in mind this number is going to be slightly off because there are a lot of other isotopes that do exist within, whether radioactive or they're unstable in nature as well. So there's actually dozens of isotopes. Do a Google search on isotopes of magnesium and you'll see a big list of them that do exist. There are a lot of them. On to another type of example that you might see with natural abundances. So with some other types of examples, sometimes you're given problems that don't quite have all the pieces of information. However, they might be easier than you realize. So for this one, it says bromine occurs in nature, mainly in the form of 2 isotopes. It says 79 bromine has a natural abundance of 49.7%. Calculate the abundance of bromine 81. Okay, so how are we supposed to do this problem? It doesn't give us like the actual numbers of mass. We could try to add it up and solve backwards using our periodic table. However, there's a much easier way of thinking about this. So being that there are 2 isotopes, what is the total percentage of all isotopes? So think about that. What could be your possible total maximum grade you can get in the class? Well, 100%, right? So being that 100% is the total, well, in this case, we have 2 individual isotopes. One of them is 49.7%, and we don't know what the other one is. So is there an easy way to go about and try to solve this? And the answer is quite frankly, yes. Just subtract the percents. So if you move things around, right, and we make it where it's 100%, minus 49.7%, it will equal our percentage that is representative of bromine. So 100 minus 49.7, and what you will get is 50.3%. This is an extremely common problem that is put on exams, on homeworks, in chemistry classes all around the country. And the number of students that overthink it, thinking they have to use the equation, they have to plug all these things in, read the problem carefully, write what's given to you, and notice what is given to you. Sometimes it's just simply writing out your full percentage, right? Because it should equal 100%. What are all your pieces? If this problem if it already gave you both percents, you could still go through and solve it like the one we did above, where we put it into our equation just like before, right? It would be one less isotope, so it'd be a little easier than the one we did earlier. I hope that this video helped, and there'll be more videos to come throughout the coming months and to help you with chemistry. And I look forward to seeing you all next time. Please hit that like and subscribe button to help support the channel. Keep it growing. It's been growing a lot. I appreciate all of you, and thank you all, and have a wonderful day. Bye now.